Falcon Heavy, previously known as the Falcon 9 Heavy, is a heavy-lift space launch vehicle being designed and manufactured by SpaceX. The Falcon Heavy is a variant of the Falcon 9 V1.1 launch vehicle and will consist of a standard Falcon 9 rocket core, with two additional strap-on boosters derived from the Falcon 9 first stage. This will increase the low Earth orbit payload to about 53 tons, compared to about 13 tons for a Falcon 9 V1.1. Due to the Falcon 9 CRS-7 failure investigation, the first launch is now expected in 2016. History. At a press conference at the National Press Club in Washington, D.C. on April 5, 2011, Elon Musk stated, "A OE Falcon Heavy will carry more payload to orbit or escape velocity than any vehicle in history, apart from the Saturn V moon rocket, which was decommissioned after the Apollo program. This opens a new world of capability for both government and commercial space missions." SpaceX originally announced that the Falcon Heavy demonstration rocket would arrive at its West Coast launch location, Vandenberg Air Force Base, California, before the end of 2012, with a launch planned for 2013. After early launches from Vandenberg, the first launch from the Cape Canaveral East Coast Launch Complex was planned for late 2013 or 2014. By late 2012, the company modified the planned first launch date to 2013. Originally, the first launch from the East Coast Cape Canaveral Launch Complex was planned for 2013, but it is currently scheduled for 2015 with the STP-2 U.S. Air Force payload. While the initial specifications of the new launcher in April 2011 projected LEO payloads of up to 53,000 kilograms and GTO payloads up to 12,000 kilograms, later reports in 2011 projected higher payloads beyond low Earth orbit, including 19,000 kilograms to geostationary transfer orbit, 16,000 kilograms to translunar trajectory, and 14,000 kilograms on a trans-Martian orbit to Mars. By late 2013, SpaceX raised the projected GTO payload for Falcon Heavy to up to 21,200 kilograms. The Falcon Heavy falls into the Super Heavy Lift range of launch systems under the classification system used by a NASA Human Spaceflight Review Panel. SpaceX states that the Falcon Heavy will be able to deliver more usable payload to orbit than any launch vehicle since the Saturn V. In April 2015, SpaceX sent the U.S. Air Force an updated letter of intent April 14 outlining a certification process for its Falcon Heavy rocket to launch national security satellites. The process includes 3 successful flights of the Falcon Heavy including 2 consecutive successful flights, and states that Falcon Heavy can be ready to fly national security payloads by 2017. As of April 2015, the SpaceX manifest has 5 Falcon Heavy launches listed, but does not show specific dates. By September 2015, and after a loss of mission event on Falcon 9 Flight 19 in June 2015, SpaceX rescheduled the maiden Falcon Heavy flight for April or May 2016. Design. The Falcon Heavy configuration consists of a standard Falcon 9 with 2 additional Falcon 9 first stages acting as liquid strap-on boosters, which is conceptually similar to EELV Delta IV Heavy launcher and proposals for the Atlas VHLV and Russian Angra. Falcon Heavy will be more capable than any other operational rocket, with a payload to low Earth orbit of 53,000 kilograms. The rocket was designed to meet or exceed all current requirements of human rating. The structural safety margins are 40% above flight loads, higher than the 25% margins of other rockets. The Falcon Heavy's design payload capacity, capabilities, and total thrust are equivalent to the Saturn C3 launch vehicle concept for the Earth orbit rendezvous approach to an American lunar landing. First stage equals, the first stage is powered by 3 Falcon 9 derived cores, each equipped with 9 Merlin 1D engines. The Merlin 1D provides a sea-level thrust of 620 kilonewtons at a specific impulse of 282 seconds, a vacuum thrust of 690 kilonewtons at 311 seconds, and is throttleable from 100% to 70%. The Falcon Heavy has a total sea-level thrust at liftoff of 17,615 kilonewtons, from the 27 Merlin 1D engines, while thrust rises to 20,000 kilonewtons as the craft climbs out of the atmosphere. Falcon Heavy has been designed with a unique propellant crossfeed capability, where some of the center core engines are supplied with fuel and oxidizer from the two side cores, up until the side cores are near empty and ready for the first separation event. This allows engines from all three cores to ignite at launch and operate at full thrust until booster depletion, while still leaving the central core with most of its propellant at booster separation. This staging system has been called asparagus staging in the popular space simulation game Kerbal Space Program. It's a term virtually unknown outside the game's community, but it comes from a proposed booster design in a book on orbital mechanics by Tom Logsdon. An engineer named Ed Keith is attributed as the creator, and he called the design an asparagus stalk booster, orbital mechanics, theory and applications. After the side cores are released, the center engine in each side core will continue to burn for a few seconds in order to control the trajectory of the side booster. All three cores of the Falcon Heavy arrange the engines in a structural form SpaceX calls OctaWeb, aimed at streamlining the manufacturing process, and each core will include 4 extensible landing legs, to control the descent of the boosters and center core through the atmosphere. SpaceX uses small grid fins which deploy from the vehicle after separation. After the side boosters separate, the center engine in each will burn to control the booster unregistered trademark S trajectory safely away from the rocket. The legs will then deploy as the boosters turn back to Earth, landing each softly on the ground. The center core will continue to fire until stage separation, after which its legs will deploy and land it back on Earth as well. The landing legs are made of state-of-the-art carbon fiber with aluminum honeycomb. The 4 legs stow along the sides of each core during liftoff and later extend outward and down for landing. Both the grid fins and the landing legs on the Falcon Heavy are currently undergoing testing on the Falcon 9 launch vehicle, which are intended to be used for vertical landing once the post-mission technology development effort is completed. Second stage equals. The upper stage is powered by a single Merlin 1D engine modified for vacuum operation, with an expansion ratio of 117:1 and a nominal burn time of 345 seconds. For added reliability of restart, the engine has dual redundant pyrophoric igniters. The interstage, which connects the upper and lower stage for Falcon 9, is a carbon fiber aluminum core composite structure. Stage separation occurs via reusable separation collets and a pneumatic pusher system. The Falcon 9 tank walls and domes are made from aluminum lithium alloy. SpaceX uses an all-friction stir-welded tank. The second stage tank of Falcon 9 is simply a shorter version of the first stage tank and uses most of the same tooling, material and manufacturing techniques. This approach reduces manufacturing costs during vehicle production. Reusable technology development equals. Although not a part of the initial Falcon Heavy design, SpaceX is doing parallel development on a reusable rocket launching system that is intended to be extensible to the Falcon Heavy, first to the booster stage and ultimately to the second stage as well. Early on, SpaceX had expressed hopes that both rocket stages would eventually be reusable. More recently, in 2011, SpaceX announced a funded development program to build and fly a reusable launch system that will ultimately bring a first stage back to the launch site in minutes and a second stage back to the launch pad, following orbital realignment with the launch site and atmospheric re-entry, in up to 24 hours with both stages designed to be available for reuse within single-digit hours after return. The reusable launch system technology is under consideration for both the Falcon 9 and the Falcon Heavy. It is particularly well suited to the Falcon Heavy where the two outer cores separate from the rocket much earlier in the flight profile, and are therefore both moving at a slower velocity at the initial separation event. As of March 2013, the publicly announced aspects of the SpaceX reusable rocket technology development effort include an active test campaign of the low-altitude, low-speed Grasshopper vertical takeoff, vertical landing technology demonstrator rocket, and a high-altitude, high-speed Falcon 9 post-mission booster return test campaign here beginning in late 2013. with the sixth overall flight of Falcon 9 every Falcon 9 first stage, which was instrumented and equipped as a controlled descent test vehicle to accomplish propulsive return over water tests. SpaceX has indicated that the Falcon Heavy payload performance to geosynchronous transfer orbit will be reduced by addition of the reusable technology, but would fly at much lower launch price. With full reusability on all three booster cores, GTO payload will be 7,000 kilograms. If only the two outside cores fly as reusable cores while the center core is expendable, GTO payload would be approximately 14,000 kilograms. Falcon 9 will do satellites up to roughly 3.5 tons, with full reusability of the boost stage, and Falcon Heavy will do satellites up to 7 tons with full reusability of the all three boost stages, Musk said, referring to the three Falcon 9 booster cores that will comprise the Falcon Heavy's first stage. He also said Falcon Heavy could double its payload performance to GTO if, for example, we went expendable on the center core. Design revisions announced in 2015. SpaceX announced a number of changes to the Falcon Heavy rockets in 2015, and intends parallel design changes to the existing Falcon 9 V1.1 launch vehicle as well. The new Falcon 9 has not yet been named, as of March 2015. The new Falcon Heavy design will utilize as the two side cores the same core as the new Falcon 9, while the center core of the Falcon Heavy will be a core with the original Falcon 9 V1.1 dimensions and structure. Design changes to the Falcon Heavy side cores will include a new propellant mix, changes to the launch vehicle thrust structure, a higher performance engine. The Merlin 1D has completed a substantive round of additional qualification testing since it was initially used in late 2013 on the initial Falcon 9 V1.1 mission Seguro, and several size and volume changes to the first stage and second stage propellant tanks. Changes will also be made to the second stage, but as of mid-March 2015, public sources on second stage detailed changes have only been explicit about changes to the Falcon 9 second stage. Pricing and development funding. At an appearance in May 2004 before the United States Senate Committee on Commerce, Science, and Transportation, Elon Musk testified, long-term plans call for development of a heavy lift product and even a super heavy, if there is customer demand. We expect that each size increase would result in a meaningful decrease in cost per pound to orbit. Ultimately, I believe $500 per pound or less is very achievable. This $500 per pound goal stated by Musk in 2011 is 35% of the cost of the lowest cost per pound LEO-capable launch system in a circa 2000 study, referenced by Spacef.com in 2001, the Zenit, a medium-lift launch vehicle that can carry 14,000 kilograms into LEO. As of March 2013, Falcon Heavy launch prices are below $1,000 per pound to low Earth orbit when the launch vehicle is transporting its maximum delivered cargo weight. The published prices for Falcon Heavy launches have moved some from year to year, with announced prices for the various versions of Falcon Heavy priced at $1 million in 2011, $1 million in 2012, $1 million in 2013, and $85 million for up to 6,400 kilograms to GTO in 2014. Launch contracts typically reflect launch prices at the time the contract is signed. SpaceX has claimed the cost of reaching low Earth orbit can be as low as $1,000 per pound if an annual rate of 4 launches can be sustained, and as of 2011 plan to eventually launch 10 Falcon Heavy and 10 Falcon 9 annually. A third launch site, intended exclusively for SpaceX private use, is planned at a site near Brownsville, Texas. SpaceX expects to start construction on the third Falcon Heavy launch facility, after final site selection, no earlier than 2014, with the first launches from the facility no earlier than 2016. In late 2013, SpaceX had projected Falcon Heavy's inaugural flight to be sometime in 2014, but as of March 2014 expects the first launch to be in 2015 due to limited manufacturing capacity and the need to deliver on the Falcon 9 launch manifest. The Falcon Heavy is being developed with private capital. No government financing is being provided for its development. By late 2013, SpaceX prices for space launch were already the lowest in the industry. If SpaceX is able to successfully complete development on its SpaceX reusable rocket technology and return booster stages to the launch pad for easier enabling even lower launch price a new economically driven space age could result. Testing. As of May 2013, a new, partially underground test stand was being built at the SpaceX Rocket Development and Test Facility in McGregor, Texas, specifically to test the triple cores and 27 rocket engines of the Falcon Heavy. Scheduled launches and potential payloads. First commercial contract, Intelsat. In May 2012, SpaceX announced that Intelsat had signed the first commercial contract for a Falcon Heavy flight. It was not confirmed when the first Intelsat launch would occur, but the agreement will have SpaceX delivering satellites to geosynchronous transfer orbit. First DoD contract, USAF. In December 2012, SpaceX announced its first Falcon Heavy launch contract with the United States Department of Defense. The United States Air Force Space and Missile Systems Center awarded SpaceX two Evolved Expendable Launch Vehicle class missions, including the Space Test Program 2 mission for Falcon Heavy, initially scheduled to be launched in 2016. The Green Propellant Infusion mission will be a STP-2 payload. It is a technology demonstrator project partly developed by the U.S. Air Force. Solar System Transport missions. In 2011, NASA Ames Research Center proposed a Mars mission called Red Dragon, that would use a Falcon Heavy as the launch vehicle and trans-Martian injection vehicle, and the Dragon capsule to enter the Martian atmosphere. The proposed science objectives were to detect biosignatures and to drill 3.3 feet or so underground, in an effort to sample reservoirs of water ice known to exist under the surface. The mission cost as of 2011 was projected to be less than $425 million, not including the launch cost. The concept was to be formally proposed in 2012/2013 as a NASA Discovery mission but was not selected. Beyond the Red Dragon concept, SpaceX announced in May 2015 that they are positioning Dragon V2 spacecraft variants in conjunction with the Falcon Heavy launch vehicle to transport science payloads across much of the Solar System, in cislunar and inner Solar System regions such as the Moon and Mars, as well as to outer Solar System destinations such as Jupiter's moon Europa. Details include that SpaceX expects to be able to transport 2,000 to 4,000 kilograms to the surface of Mars, including a soft retropropulsive landing using Super Draco thrusters following a limited atmospheric deceleration. When the destination has no atmosphere, the Dragon variant would dispense with a parachute and heat shield and add additional propellant. See also, Comparison of orbital launchers families, Comparison of orbital launch systems, Delta IV Heavy, List of Falcon 9 and Falcon Heavy launches, Saturn C3, Space Launch System. References. External links, Falcon Heavy official page, Falcon Heavy flight animation, January 2015.